You know that feeling when you grab a bottle of fresh juice, but it has this, I don't know, a slightly cooked taste? Well, today we're going to get into why that happens. And more importantly, how electricity is totally changing the game, moving us away from brute force heat to something way, way smarter. Let's get into it.
Right? Have you ever noticed this? You buy something that's supposed to taste like it was just squeezed, but there's a hint of something else there. It's subtle, but it's there. Well, you're not imagining things. That little detail is actually the key to this whole story.
Okay, so for forever, the main way to make food safe has been traditional pasteurization. Basically, you just heat it up to kill all the bad stuff. And look, it works. It makes food safe. But that heat is kind of like a blunt instrument. It doesn't just kill germs, it also damages delicate flavors, it can destroy vitamins, and it messes with the texture. The dream, the real goal, is to get that same level of safety, but keep all that fresh-like quality we actually want. And that's where things start to get really interesting. So here's our game plan for today. First, we're going to dig into why heat is a problem. Then we'll see how electricity comes to the rescue. We'll meet our three high-tech contenders: pulsed electric fields, microwaves, and ohmic heating. And then, of course, we'll get to the final verdict. All right, section one, the problem with heat. Think about it like this. Imagine you have one little weed in your garden, and to get rid of it, you use a giant flamethrower. I mean, yeah, you'll definitely get the weed, but you're probably going to scorch everything else around it too. That's kind of what we're doing with heat. And let's be honest, we as consumers are driving this whole thing. We want food that's safe, of course, but we also want it to taste amazing, to have all of its nutrients, to feel fresh. The food industry knows this, and they know that just blasting everything with high heat isn't going to cut it anymore. And that brings us right here. If heat is the big, clumsy flamethrower, then electricity is like a surgical laser. It's all about being more precise, more targeted, and just gentler on the food. So here is the really big question. What if, instead of cooking the entire product just to kill a few germs, you could just zap the microbes directly? Well, that's exactly what three incredible technologies are designed to do. So let's meet our contenders. First up in the ring, we have pulsed electric fields, or PEF for short, and you gotta love this title, the Precision Strike. It just perfectly sums up what this is all about. This isn't a carpet bomb, this is a targeted attack. So what exactly is PEF? Well, it's what we call a non-thermal method. It sends these super short, really powerful pulses of electricity, we're talking microseconds long, through a liquid. Instead of heating everything up, these pulses go straight for the microbes and basically poke holes in their cell walls. It's a process called electroporation. And this is exactly how it works, step by step. First, you apply the electric field. That makes the microbe's membrane stretch out. Then tiny little pores start to form. And with enough voltage, those pores just rip open. The membrane ruptures, and poof, the cell is gone. It's a really elegant, and for the microbe, a very lethal attack that happens in the blink of an eye. And this isn't just some concept in a lab. This is what the actual hardware looks like. The juice, or whatever liquid it is, flows through these special chambers. The different designs you see are all about making sure that every last drop gets hit with that electric field uniformly and efficiently. This is how you take that cool science and turn it into a real industrial process. And this number right here, this is the magic number. This is the whole point. The total temperature of the food only goes up by about 5 to 15 degrees Celsius. That's it. It's barely even noticeable. And that is exactly why it's called a non-thermal method. You get all the safety without any of the damaging heat. Okay, so let's break down PEF. The pros are huge, right? It keeps the flavor, keeps the nutrients, it's super fast, and it kills a ton of microbes. But there are some cons. It's not great against these really tough things called bacterial spores, which is why the food still needs to be refrigerated. It also pretty much only works on liquids for now, and the official regulations are still playing catch-up. All right, let's bring on our second contender. And this is one you definitely know: microwave heating. But we're not just talking about your kitchen microwave. When you scale this up, it becomes a really powerful tool for the food industry. So we all know microwaves heat food fast, but how do they actually do it? Well, they shoot out these electromagnetic waves that grab onto polar molecules, especially water, and make them flip back and forth, literally billions of times a second. It's like they're making all the water molecules dance. All that movement creates friction, and that friction creates heat. It cooks the food from the inside.
The pros are pretty obvious. It's super fast, it's efficient, but the cons? The cons are a really big deal, especially for safety. We've all experienced this, right? You get those infamous hot and cold spots. And a cold spot in industrial food processing isn't just annoying, it could be a safe zone for germs to survive. That uneven heating is really the Achilles heel of using microwaves on a big scale.
And that leads us to our final contender, ohmic heating. And the title here says it all: the food heats itself. Now, this one is really cool because it solves that whole uniformity problem in a pretty brilliant way. So, how on earth does food heat itself? Well, instead of shooting waves at the food, ohmic heating passes an electric current directly through the food. And since food has some natural electrical resistance, it heats up when the current flows through it. The key here is that the food literally becomes its own heating element. Every single particle heats up at the exact same time. The biggest win for ohmic heating is that incredible uniform heat. This makes it absolutely perfect for tricky foods like chunky soups, where you need to make sure the carrots, the chicken, and the broth all get to the same safe temperature. It's also really fast and efficient. The main catch? The food has to actually conduct electricity, so it won't work on something like pure oil. Plus, the electrodes passing the current can get gunked up, so they need to be cleaned. Okay, we've met our 3 contenders. Each one is a powerhouse in its own right, with some serious strengths and some very specific weaknesses. So, who wins the battle? It's time for the final verdict. And this table really lays it all out. It turns out there isn't one single winner. The real answer is that it's all about choosing the right tool for the right job. If you want to keep that fresh taste in your juice, PEF is your champion, no question. If you just need to reheat something fast, the good old microwave is your go-to. And if you're making something complex, like a chunky stew, ohmic heating is the absolute star of the show. Each one has its own perfect place to shine. And this quote from the source material really hits the nail on the head. We haven't just found one replacement for pasteurization. What we've really done is develop a whole new toolkit for food scientists. Now they can look at a specific food and pick the absolute best technology to make it safe while keeping it delicious. So I'll just leave you with this question to think about. As these technologies get even better and cheaper and more common, what's next? Are we going to see milk that tastes like it's straight from the dairy but lasts for weeks? Soups that have perfectly crisp, fresh-tasting vegetables? The possibilities really are electrifying. Thanks for joining me.